Hello everyone, my name is Anil Sani, and today I would be presenting our lecture on temporal probability models. This lecture is part of a course at Cedar Sinai titled Artificial Intelligence HAI 100B. Let's dive into the fascinating world of temporal modeling for computational biomedicine. Here is our roadmap for today's lecture. We will be beginning with an introduction to the topics of temporal probability models, or TPMs for short. Then we will cover four main inference tasks, starting with filtering, prediction, smoothing, and ending with most likely explanation. Next, we will be discussing three main types of TPMs: hidden Markov models, Kalman filters, and finally, dynamic Bayesian networks. Let us set the foundation of TPMs with some key definitions and terminology. Temporal probability models lets us capture how a system changes over time. That is, TPMs describe the probability distribution of a system at different time steps. Think of an AI agent in a world where it cannot see everything and has to make smart guesses as it goes. In other words, agents are working in uncertain environments over time. And we need a representation to keep track of this information and reason about it. For example, diabetes management is a type of temporal probability model, whereas vehicle diagnosis is not. Managing diabetes means tracking blood sugar as it fluctuates, using test results and symptoms as clues. In contrast, when repairing a car, we assume that whatever is broken remains broken during the process of diagnosis, and our job is just to infer the state of car from the observed evidence, which also remains fixed. So in such time-dependent domains, we need a framework to represent both the uncertain system state and the evidence we collect at each point. For that, we define xt as the set of unobservable state variables at time t. For example, in our case of diabetes management, it can be blood sugar at time t, stomach contents at time t. And we also include a set of observable evidence, that is ET, at given time t. These are the observations we make. For example, measured blood sugar level, pulse rate, etc. Some more clarifications when it comes to nomenclature. First, we assume discrete time steps. That is, we take measurements at regular time intervals. We typically write XAB to mean the collection or the sequence of variables XA, XA plus 1 up to XP. Other things to note here is XT is a set of variables. It may or may not be a single variable. XT is a set of variables such as XT1, XT2, and so on. Second, XT and XT plus 1 are different variables. They are not the same variables at two different times, even though XT plus 1 can depend on XT. Small xt is the assigned value of xt, and similarly small et is the value that has been assigned to et. Now, technically, xt can depend on all the previous system states from 0 to t minus 1. But that would make the analysis way too complicated, especially when the value of t becomes high. Therefore, we make an assumption called the Markov assumption, where the current state depends on a fixed and finite number of previous states. Using that assumption, we can define multiple types of Markov processes. In first order Markov process, for example, we can say that xt depends only on xt minus 1. In mathematical terms, we can write it as probability of xt given x 0 to t minus 1 is probability of xt given xt minus 1. In a network form, we can represent it as this, where there is only one incoming and only one outgoing arrow from any given variable. Similarly, in a second order Markov process, we say that xt depends only on xt minus 1 and xt minus 2. Graphically, we can represent it as in this form where for each variable, there are two incoming and two outgoing edges. This is the simplified schematic we would be using throughout this lecture. As mentioned earlier, xt, xt minus 1, xt plus 1, and so on are state variables. Et, et plus 1, et minus 1, and so on are the evidence variable. Transition model refers to the probability distribution of xt given xt minus 1. And sensor model similarly describes the dependence of the evidence variable on the state variable. Let us look at this graphical model in some more detail. In this simplified network representation, each state depends only on the previous state, as shown by the arrows between x variables. We make a few assumptions here. The first assumption is sensor Markov assumption, which clearly states that the evidence at time t depends only on the hidden state at that time. In other words, probability of ET given all the state and evidence variables is only the probability of evidence variable given that state variable. The second assumption we make is that both the transition model and sensor models are fixed for all time steps. That is, we are working with stationary processes. Using the Markov assumptions and Bayesian networks that we have studied in previous lectures, we can write the joint probability distribution of all states and all evidences as this. Px0 to t, E1 to t is equal to probability at x0 and then the multiplication of probability of xi given xi minus 1 and probability of ei given xi for I1 to t. The exact derivation of this formulation is beyond the scope of this lecture, but I wanted to write it there to make the point that this factorization is what makes inference in temporal models computationally tractable. Now consider the following example of a TPM. Assume you are a security guard stationed at a secret underground installation. You want to know whether it's raining today, but your only access to the outside world occurs each morning when you see the director coming in with or without an umbrella. So for each day, the set ET contains a single variable called umbrella T or UT for short, and set XT contains a single state variable, rain T or RT for short. The transition model and the sensor models have also been filled up with some reasonable values in this example. We would be using this example multiple times in other slides as well. Markov assumption is unfortunately not without some drawback. Mostly because first order Markov assumption is not exactly true in the real world. In the example prior, we assumed that the probability of rain today depends only on whether it rained yesterday. In the real world, however, whether or not it rains today depends on many other factors. There are some obvious fixes to this issue. We can increase the order of Markov processes and say that whether or not it rains today depends on whether or not it rained yesterday and the day before and so on. Or we can add other state variables such as temperature at T, pressure at T, and so on. Once we have a temporal model, we can ask several kinds of questions, or in other words, we can do reasoning over TPMs. The first inference task we can do is called filtering, which basically means we can compute the current state, or we can estimate the current state given the evidence we have so far. Mathematically, it is written as probability of xt given E1 to t. we can do prediction. That is, we can estimate future states given the current evidence. Mathematically, we can write it as probability of x t plus k given e1 to t for k greater than 0. We can do smoothing, which basically improves estimate of the past states after seeing more data. That is, we compute probability of x k given e1 to t for k less than t. And finally, we can compute most likely explanation, which basically says that given a sequence of observation, we have to find the sequence of hidden states most likely to have generated those observations. Mathematically written as argmax over x1 to t, px1 to t given e1 to t. Let us now discuss filtering in some more detail. Filtering essentially computes the posterior distribution over the current state given all the evidence so far. That is, we have to compute pxt given 1 to t. Pictorially, we can represent it as given in the figure. Before proceeding further, we should revise two key concepts. One is generalized Bayes rule, which is basically Bayes rule with conditioning on one more variable called E here. Second, as we have learned before, Markov property of evidence says that the current evidence only depends on the current state and nothing else. So here our task is to devise a recursive state estimation algorithm for filtering. In other words, we have to come up with a formulation such as this, where probability of xt plus 1 given e1 to t plus 1 is a function of the previous state pxt e1 to t and the new evidence. So let's try doing that. We can first divide up the evidence to 1 to t and then t plus 1. Now, after using Bayes rule, we can write it as this. And now, since we know that the current evidence in the second term et plus 1 depends only on the current state, that is xt plus 1, we can simplify it further, and that gives us the final formulation. Now let us look at this formulation in more detail. This is what we have come up with so far. We can rewrite the second term by conditioning on xt. Remember, xt means we already know the value of that state. Now, as you can see, xt plus 1 should only depend on xt. So we can simplify it like this. Now, as you can see, these three terms mean something, and we have seen them before. The term after alpha is the sensor model, probability of evidence given the state. The next term is transition model, and the next term is the recursive term. We can also think of the filter estimate, the prior filter estimate pxt given 1 to t as the message f1 to t that is propagated forward along the sequence. This recursive structure makes filtering computationally efficient. That is, the message at 1 to t plus 1 is alpha forward f1 to t et plus 1, where f1 to t is what we have specified before. Now let us turn to the task of prediction. As mentioned earlier, we have to compute probability of xt plus 1 given e1 to t. That is the posterior distribution over the future states given evidence that we have received so far. And pictorially, we can represent it as this. Prediction works almost exactly like filtering, except we do not incorporate new evidence. That is, probability of xt plus k plus 1 given e1 to t can be written in a summation form like this by conditioning on xt plus 1 k. And as we know, the first term is the transition model and the second term is the recursive step. So we basically repeatedly apply the transition model on the recursive step. Over long time horizon, the state distribution often converges to a distribution commonly known as the stationary distribution. Let's now turn to the task of smoothing. As mentioned earlier, we have to compute probability of x k given 1 to t when k is less than t. That is the probability of an earlier state given evidence to date. We are basically trying to improve the estimate of the previous states using smoothing. For this, we can divide the evidence 1 to t into 1 to k and k plus 1 to t in the formulation. After dividing the evidence, we can use the generalized Bayes rule, and then we can use the Markov property of evidence to come with a final formulation alpha f1 to k and b k plus 1 to t. Here we define a backward message b1 b k plus 1 to t, similar to how we define forward message f1 to k. The forward message can be computed by filtering forward from 1 to k, and the backward message can be computed recursively backward from t. Let us now turn to the concept of most likely explanation. The most likely explanation task asks what sequence of states most likely generated a given set of observations. An important subtle point is that the most likely sequence of states is not the same as choosing the most likely state at each time step individually. Instead, we compute the most probable entire path through the state space. The most likely path to each xt plus 1 is the most likely path to some xt plus one more step, mathematically given as this. As you can see, this is very similar to the formulation we came up for filtering, except here f1 to t has been replaced by m1 to t, which we define as maximum over f x1 to t minus 1, probability of x1 to x t minus 1, xt e1 to t. This m1 gives the probability of most likely path to current state, and it works like a message that is updated at every time step. And incidentally, updating messages in this way is what gives us the Viterbi algorithm to figure out the most likely explanation. This method to find most likely explanation is used in many applications, such as speech recognition, where we have to find the most likely sequence of words given a series of sounds, and denoising, where we have to reconstruct bit strings transmitted over a noisy channel, among many other applications. Let us now discuss three different types of temporal probability models. The first one being hidden Markov models. A hidden Markov model, or HMM for short, is one of the simplest temporal probability models. In an HMM, the hidden state xt is given by a single discrete variable. Usually, et is also a single discrete variable. Xt has a domain of 1 to s, that is, it's finite. In HMMs, transition matrix T specifies the transition probabilities such that Tij is the probability of xt being j given xt minus 1 is I. For example, for the umbrella world we have seen before, one can write the transition probability as given in the slide. Similarly, sensor matrix OT can be constructed from the sensor probabilities. Sensor matrix is constructed for each time step and is S by S sized. In sensor matrix, diagonal elements are probability ET given XT is I. So for example, in the umbrella world, if U1 was true, O1 can be written in this way. Now, why do we need to represent everything in matrix forms? This is because the representation in the form of matrices makes filtering and other inference tasks very efficient. Now, I'm not going to go into how we derived these forward and backward messages, but just want to point out that both forward and backward message can be represented as products of different matrices. And since there are many efficient matrix multiplication algorithms that exist in the literature, these tasks, such as filtering, prediction, etc., are more efficient in this way. Let us now turn to the second category of temporal probability models, that is Kalman filters. Kalman filters extend the ideas of hidden Markov models to continuous variables. Remember, for HMM, we only used discrete variables, but for Kalman filters, we can use continuous variables. So for example, if you want to track a flying bird or any flying object, we can have 3 state variables for position and 3 for velocity. And remember, all of these variables can have continuous values. Kalman filters have been used in reasoning about the trajectories of airplanes, robots, ecosystems, planets, etc. For Kalman filters, we make some assumptions. First, we assume linear Gaussian distribution. This means that the next state, xt plus 1, should be a linear function of the current state xt plus some Gaussian noise. In practice, this looks like this. P xt e1 to t is Gaussian and the transition model is linear Gaussian. If you satisfy these assumptions, prediction can be given by this. Remember, instead of summing over xt, we are integrating over xt. The updated distribution, that is pxt plus 1, given e1 to t plus 1, can be simply given by this formulation that we have seen before. It turns out this updated distribution is also Gaussian in nature. Now we turn to the last category of temporal models that we are planning to discuss, that is dynamic Bayesian networks. Dynamic Bayesian networks generalize temporal models even further, and we have already seen some examples of dynamic Bayesian networks, that is Kalman filter and HMMs. Dynamic Bayesian networks is generalized in the sense that xt and et can contain arbitrary many variables. In fact, every time slice can have different numbers of variables. But for simplicity here, we would assume that the variables, their links, and their condition distributions are exactly replicated from slice to slice. And dBn represents a first order Markov process, such that each variable can only have parents in its own slice or the preceding slide. Let's now take an example for a dynamic Bayesian network. That is, we want to monitor a battery-powered robot moving in XY plane. And for that, we can have state variables that gives us the position of the robot as well as the velocity of the robot. We assume some method of measuring position, perhaps a fixed camera or a GPS, yielding measurements ZT. The position at the next time step depends on the current position velocity, whereas the velocity at the next step depends on the current velocity and the state of the battery. For that purpose, we also include battery T that represents the actual battery charge level, and B meter T that gives us the measurement of the battery charge level. Now, one thing to note here is that every hidden Markov model is a single variable dynamic Bayesian network. And every discrete dynamic Bayesian network can be converted into HMM if we combine all state variables in a DBM into a single state variable in HMM. For a process with n discrete variables, where each variable can have up to d values, HMM representation needs a transition matrix of size order of d raised to power 2n, and DBN requires a transition matrix of size order of n d raised to power k. For 20 state variables and 3 parents each, DBN will have 160 parameters, whereas HMM will have 10 raised to power 12 parameters. And that is the reason why we don't always use an HMM representation. HMM requires much more space, and hence it is much more expensive to do inference tasks on HMM. Now, when compared with Kalman filters, every Kalman filter can be represented in the form of a DBN with continuous variables. But not every DBN can be represented by a Kalman filter. This is because in a Kalman filter, the current state distribution is always a single multivariate Gaussian distribution. DBNs, on the other hand, are made to model arbitrary distributions. Also, real world requires non-Gaussian posteriors, and that is why we use dynamic Bayesian network. For example, if one were to model the location of my keys, it would be a difficult task with using just one Gaussian distribution. Since my keys can be in my pocket, on the bedside table, or on the kitchen counter, or in the car, a single Gaussian bump that included these places would allocate significant probability of the car's keys being in the midair above the front garden, which would be very difficult to analyze. And hence, there are aspects of the real world, such as obstacles, that introduce non-linearities, and that requires the combination of discrete and continuous variables, and that is why we need dynamic Bayesian networks. After discussing 4 inference tasks and 3 types of TPMs, I want to close the discussion by describing 2 possible applications of what we have studied so far. Kalman filters have been used as an estimator to track and predict blood glucose levels from noisy continuous glucose monitor data. As now CGM measurements gives us glucose levels every few minutes, but the measurements themselves can be noisy and delayed. But to prevent hypoglycemia, the system must estimate the current true glucose level, estimate the rate at which glucose is changing, and predict future glucose levels to trigger an early alarm. Since Kalman filters can model continuous variables, these models have been used in hypoglycemia prediction and detection using CGM. Prior to the advent of large language models used to be handled by probabilistic processes such as hidden Markov models. The idea is this: we can write the probability of a given sequence of words as probability of W1 to Wn, these are the words, and it can be given by the product of probabilities Pwi given all the words seen so far. If we were to model this in a hidden Markov model, we can write the second term as simply Pwi given Wi minus 1. Or in other words, the current word depends only on the preceding words. In such a background model, we can train such a model by counting all word pairs in a large text corpus to come up with these probabilities. But these days, as we all know, large language models can do a far better job as language models than hidden Markov models. In conclusion, we discussed temporal probability models, which provide a way of representing and reasoning about probabilistic temporal processes. TPM involves a set of random variables to represent the state at each point in time. Representations can further be simplified by making some assumptions. The first assumption being the Markov property, that is, the future is independent of the past given the present. And time homogeneity, that is, processes of change themselves do not change over time. A TPM contains a transition model that describes the evolution of state and a sensor model that describes the observation process. We discuss four principal inference tasks: filtering, prediction, smoothing, and computing the most likely explanation. And we also discussed in some detail three temporal probability models: hidden Markov models, Kalman filters, and dynamic Bayesian networks. The following book has been used as a reference for figures and text for this presentation. Thank you.